Hello, everyone. So we are supposed to start in 1 minute, but I don't see the speaker yet. Oh, no, he's here.
Maybe we can wait for a few minutes.
Mm-hmm. Nikita, maybe you can try whether everything is working.
Sorry?
Maybe you can try whether everything is working, whether we can see a screen.
Okay. 1 minute.
Mm-hmm.
Dmitry, I think you should allow me to demonstrate my screen.
Does it work now?
There is a button purity. Okay. Now I can demonstrate the screen.
So I guess everything is ready. So let's start. So today we have Nikita Kolganov from ITMP, and he will talk about a generalized unimodular gravity. So please begin.
Okay. Good evening. First of all, I would like to thank the organizer of this seminars and Dmitry Ponomarov in particular. And in today's talk, I would like to discuss particular modified gravity theories, which I call constraint modified gravities in this talk. The particular and maybe known class of such theories is the generalized unimodular gravity theories. So it is the plan of my talk. And first of all, I would like to review well-known modified gravities, its motivations, on some other features. Next, I would like to define what is the constraint modified gravities. Further, I'm going to quantize such series because such in original setup it is not general covariance series. Next, I would like to show that generalized unimodular gravity, which was proposed some years ago, is a particular class of constraint modified gravity series, and it has interesting cosmological applications. Then I will show that constraint modified gravities include not only generalized unimodular gravity, but some other interesting theories. And finally, I would like to provide some further ideas about this topic. So let's begin. Why we would like to modify general relativity? The motivations are that general relativity perfectly describes physics at intermediate scales, but in large scales it cannot naturally describe its accelerating stage of cosmological expansion, and it's not renormalizable at small scales, I think. And the most of modified gravities is are such series that it provides UV completion of generalized or of general relativity, or provide a modification such that it naturally describes late time acceleration of our universe. So let's discuss what are these modifications. There are various ways to modify general relativity, but the most obvious is to just add some additional degrees of freedom, which interacts only gravitationally. So the first way is to explicitly add gravitational interaction fields, like in scalar tensor series. The most known series are Hordesky series, Kaisens, and some other thousands of them. We can also add some vector degrees of freedom. It's usually called ether or Einstein ether theory, and we can add some super partners or maybe other degrees of freedom. In the cases when we modify gravity in such a way that it's not general relativity plus some degrees of freedom, it's often possible to reformulate the theory in such a way that resulting theory is general relativity plus some new field. It's well known that f of r gravity is an example of such idea. And the other way to modify general relativity is to break general covariance. It's also almost always equivalent to addition of some new degrees of freedom, because general covariance allows us to gauge out some of metric degrees of freedom, and when general covariance is partially or totally violated, we cannot do this, and these metric coefficients become dynamical. So, what are examples of such breaking of general covariance? I think the most known example is Horev gravity. In this theory, general covariance is broken to coordinate in time-dependent special diffeomorphisms and time-dependent reparameterization of the time. In this theory is also implied imbalance in space and time scaling dimensions. This imbalance allows us to make Copley constant dimensions being non-negative. So the new invariants of the theory are scalars composed of curvature tensor, three-dimensional curvature tensor, and extrinsic curvature tensor. So the resulting theory becomes power counting renormalizable. So the next example of non-general covariant theory is massive gravity, or so-called self-gravitating media. The basic idea is that well-known Pauli fields massive gravity theory exhibit Van Dam Veltman-Zakharov discontinuity, which doesn't allow us to use this massive gravity theory as a theory of long distance effective gravity theory. So the basic idea is to make massive term of such massive gravity theory is non-Lorentz covariant, and in general case it can non-linear case, it can arbitrary algebraic function of metric coefficient. And the last version of breaking of general covariance is modified gravities, which I'm interested in, and it is constrained modified gravities. I will discuss it in the next slide. Maybe any question at this point?
Concerning the first point on this slide, do you have Lorentz invariance or covariance?
There is Lorentz invariance of Horev gravity is broken to special rotations, while general covariance is broken to time-dependent special diffeomorphisms.
And how do you do quantum field theory without Lorentz invariance?
So in the most solid-state models are not Lorentz covariant, and they use quantum field theory. I think Lorentz invariance is not necessary to make field theory quantum.
Okay, I see. And concerning the second point, so as far as I know, there are massive gravities which don't break Lorentz covariance or invariance. I mean, like the Ram Gabadadze Tolly at least it looks Lorentz covariant in some formulations. Maybe you can give fixed gauges or do something.
Their T gravity, I think, is non-Lorentz invariant, Lorentz covariant in the original formulation, because it explicitly introduced Minkowski or some other reference metric, and massive term.
Yeah, but metric, Minkowski metric is Lorentz invariant.
Ah, okay, okay. I think it means that Lorentz non-Lorentz invariant non-Lorentz invariant massive term in massive gravity is not only a solution to discontinuity problem.
I see.
Maybe it's the answer.
Mm-hmm.
Okay, let's proceed. So let's define constraint modified gravities. I call constraint modified gravities the gravities which differs from general relativity by some algebraic constraint on metric coefficients, which I denote U of metric equal to 0. So nearly this constraint should decrease the number of degrees of freedom, but this conclusion is very naive, because in gauge theory the constraint is usually increases the number of degrees of freedom. It is because such constraint is usually second class constraint, which is not which doesn't compute with generators of diffeomorphisms, so it leads to imbalance in the number of second and first class constraint. So consequently, degrees of the number of degrees of freedom usually increases. I will comment this point in the next slide. But from the pure Lagrangian point of view, such constraints breaks general covariance, so we cannot use part of diffeomorphism to gauge out part of metric degrees of freedom. So the Lagrangian formulation of such constraint modified gravities is the following. The action consists of Einstein-Hilbert action plus Lagrange multiplier part, which is Lagrange multiplier multiplied by the constraint U of G mu. So all we know that at least at low energies, all series should be Lorentz invariant and maybe Lorentz covariant. So we should covariantize such a series to make it Lorentz invariant. It always can be done by means of four Stackelberg fields, which I denote phi superscript A capital, and the covariantizing procedure are the following. We do the change of coordinates from x to phi. So after this change of coordinates, Einstein-Hilbert term is invariant. The local measure is also invariant, but argument of constraint function u becomes new metric, which I denote capital C AB, which is diffeomorphism transformed initial metric G mu. Now, if one treats Stackelberg field as a scalar and also Lagrange multiplier lambda as a scalar, this action becomes general covariant. Any questions?
Can I ask a question, please? You change coordinates xa, where a runs from 0 to what? Is it the same index?
From 0 to 3. No.
So it's 4-dimensional coordinate.
Yep. The number of Stackelberg fields equals to the number of space-time coordinates.
So just the coordinate change of the original local coordinates x mu.
Is it not what is called parameterization? You can start with any field theory and then just introduce new copies of coordinates as Stückelberg fields for which diffeomorphisms are gauge symmetries, and you make any gauge theory into diffeomorphism invariant. That's the standard trick. That's what is being done, if I understand correctly, right?
Right.
Okay.
The gauge in which phi a becomes initial coordinates xa brings us back to initial formulation, non-covariant formulation. However, to prove that covariantized theory and non-covariant theory are equivalent, we should do the following. We should show that Stackelberg fields doesn't introduce any new dynamics. Let us show this. We write down the stress energy tensor, which is generated by Lagrange multiplier term. The question is, do you see my mouse point?
Yeah.
Okay. So I can use it. We have this stress energy tensor. So using the Bianchi identities, it should conserve. Also, we can use constraint equation. So two such equations lead to the fact that Stackelberg fields equations of motion automatically satisfy. The only condition is that the change of variables to coordinates phi a is not degenerate. We quantize our theory, and now we would like to concentrate on the particular theories or on the particular types of constraints U. We restrict ourselves to such functions U of CAB, such that the resulting theory is rotational invariant under rotations of spatial Stackelberg fields. And the second restriction is that stress energy tensor generated by Lagrange multiplier term becomes a perfect fluid stress energy tensor. That is, it has the following form.
What are P and Q and rho in this equation?
It can be found from the function U. if there is a well-known classification of such type of Lagrangians, but there are so-called self-gravitating model that differs from our constraint modified gravities by the absence of this Lagrange multiplier. So the action of self-gravitating media model is an constant Hilbert term plus such I think mass term of the following form. Such class of modified gravities I will study it and classify it. So there are only two possible functions U of CAB, so that stress energy tensors becomes stress energy tensor of some perfect fluid, and so I can more. And this pressure and this density can be reconstructed from the form of these these functions V1 and V2. In the next slides, I provide you explicit formula for P and rho.
Can I ask a question?
Yep.
Why do you request that the stress energy tensor has this perfect fluid form? What's special?
I think this restriction is because such type of series are more interesting from the cosmological ground. We know that cosmology is rotationally invariant and can be effectively described by perfect fluid. I think it is the motivation of such restriction.
But
Okay,
I guess
true that. Sorry, Dima.
But I guess in the actual cosmology, this P and rho, it comes from the actual matter, right? And you're trying to mimic it by the deforming gravity.
Yep. We try to mimic non-trivial matter content from pure metric degrees of freedom.
But why? So I guess it works already, like I mean, with matter. Why do you want to incorporate it into deforming gravity?
I don't know how to answer this question.
Dark matter maybe could be.
But I can tell you that when we add some maybe dark matter and some other matter content, we should answer the question: what is this matter? And we can answer the question as follows: this maybe dark matter or dark energy is some part of metric content.
Okay, I see. So you say that at least part of matter in principle can be, like part of P and rho can originate from gravity itself.
So in this formula, P and rho are functions of Stackelberg fields, and in non-covariant gauge phi equal to x, it is just a function of metric coefficients.
Okay, thank you.
Okay, thank you. Так, let us concentrate on the first type of constraint. So let us consider this type of constraints. The first of all, we will discuss it in a non-covariant setup. So we should do non-covariant gauge so that this constraint can be rewritten as the following equation on metric coefficients. So zero component of contrariant metric is some function n of determinant of special metric. Oh, sorry. The function n of gamma can be reconstructed from the explicit form of function v. It is just a rewriting of this constraint. General relativity equipped by this type of constraint is nothing but generalized unimodular gravity, which was recently proposed by Barvinsky and Kamyshik a few years ago. So in the next years, this theory was extensively studied by me, Barvinsky, and some other people. And in the next couple of slides, I would like to discuss this generalized unimodular gravity. And after that, I would like to make a new conclusion, which leads from covariant versions of this theory.
May I ask a question?
Yeah.
So what is the parameter? You break general covariance, but which is the parameter here?
The parameter of the theory is a function n of gamma. It is a functional parameter of the theory.
Okay, so the question could be that, for example, gravitational waves, which seem to be consistent with.
Okay, I understand the question. I'm answer it in the following way. We can write down the equation of motion of this theory in the following way. It's a tensor G mu nu, it's an Einstein tensor, multiplied by some tensor which has the property of projector, P mu nu rho sigma. So if G mu nu equals to 0, it means that equation of motion of such modified theory are also satisfied. So gravitational waves comes from this type of equations. So we can see that in our modified theory there are also usual gravitational waves, but because the rank of this tensor is not maximal, there are also some additional solutions.
But you have constraints, so are you saying that transverse modes are not modified? Is that what you're going to say?
Okay, if we consider perturbation theory of this type of model, we indeed found that tensor content that action of transverse traceless mode is the same as in general relativity. So tensor content, transverse traceless tensor content is not changed.
Okay, so you'll see the difference at nonlinear level, not on.
I don't know. We
Okay, all right.
didn't do these calculations, but at linear level, it indeed doesn't change.
Well, the issue is, of course, whether there exists scalar or something like scalar degrees of freedom here.
Yeah, we have additional scalar degree of freedom, and in the next slides, I would like to interpret it, and next, I would like to make a connection between this model and well-known K-essence model. I can tell you that this theory is equivalent to particular K-essence model. So that this additional scalar degrees of freedom is a scalar of some K-essence theory.
Okay.
The original motivations for such a model was again rotational variance and perfect fluid property of stress energy tensor. But these authors didn't find the analogy with self-gravitating models and corresponding classification of Lagrangian, and the first type of constraints was found by the second, which correspond to V2 of B, and that was lost. So in the we discuss also the second type. So let's proceed.
One more question, please.
Yep.
On the previous slide, could you please explain the statement that this unimodular gravity is equivalent to GR with cosmological constant as a global degree of freedom?
So it's our generalized unimodular gravity becomes unimodular gravity, usual unimodular gravity, when n of gamma takes particular form 1 over square root of gamma. So in this unimodular gravity, the only additional degree of freedom is cosmological constant. I can explain it as follows. So we can do formal change of variables under, I think, path integral, which where we assume some type of gauge d mu d lambda, which is Lagrange multiplier integrated with the x S Einstein-Hilbert plus lambda square root of d minus 1. So in the case when n of gamma equals to 1 over square root of gamma, it can be rewritten as square root of 4-dimensional metric equals to 1. It is because it's called unimodular gravity. So we can do formal change of variables and found the following: that this functional integral becomes integral over some vector field. Oh, sorry. Some vector field V mu over Lagrange multiplier lambda and over matrix with density x minus s constant Hilbert minus v lambda plus partial derivative of lambda. So if one integrates out vector field v mu, lambda becomes constant. It's a Lagrange multiplier times gradient of lambda. So this integration can be written as integration over g mu and finite dimensional integration over lambda, zero mode of lambda. Is it the answer on your question?
Okay, so roughly speaking, one of propagating fields is constant on shell, and it can be treated as a cosmological constant, right?
Yeah.
Okay,
It's true.
Can I also ask one naive thing? So what happens if you just fix the gauge? So you start from GR and you just fix the gauge where determinant of G is 1. So is it related to unimodular gravity or not?
In such when you fix the gauge, you should also add some Faddeev-Popov or some other measure factor. But when we add this type of constraint, we do not assume any additional Faddeev-Popov multiplier in the measure of functional integration. So also I can explain it as in gauge systems, when you would like to fix the gauge, you should also restrict yourself that on shell Lagrange multiplier near the gauge should be 0 on shell. But here we see on the example of unimodular gravity, it can be non-zero but constant. It is a difference between.
But is it correct that if you are interested in gauge inequivalent solutions, then those of if you take usual gravity, impose gauge conditions that determinant equals to 1, and take residual gauge symmetries, this theory will have exactly the same space of inequivalent solutions, classically at least, as the one where you impose this constraint with a Lagrange multiplier. So classically they seem to be equivalent, or what is wrong? The space of solutions is the same, right? Because any solution you can take it, make a diffeomorphism and bring it a modulo of course local issues.
In general relativity or in our model?
And it's gauge transformation. So each solution of gravity is a solution of unimodular gravity.
All the solution of gravity is the solutions of unimodular gravity under diffeomorphism equivalence. But in I can explain as follows: this type of constraint cannot be the gauge because it doesn't totally fix the gauge freedom. Faddeev-Popov determinant becomes degenerate with such type of gauge or constraint.
Yeah, but it's a partial gauge, of course. You still have different
So
volume.
if we equip with some other gauges, it is still degenerate, I think.
No, wait a second. I think the point is that, generally speaking, you can't use the gauge condition in the Lagrangian. You first vary the Lagrangian with respect to everything, and then impose the gauge. You can't do this in the opposite fashion, because then you will lose part of field equations. Okay, so the unimodular gravity with square root of g imposed equal to 1 has less equations, and it turns out that in this theory is equivalent to general relativity with arbitrary cosmological constant. So the number of the set of solutions is different. In GR, you have just zero cosmological constant or fixed number as a cosmological constant. Here, the cosmological constant can be arbitrary, just a number, an arbitrary number. A cosmological constant is a characteristic of solutions, not the theory. So here, in unimodular gravity, you have more solutions than in GR with a particular cosmological constant.
Yeah, I think Nikita said the right words. Yeah, I agree that this is not like gauges imposed. At the classical level, you don't add Lagrange multiplier constraint because that modifies Einstein equations. Usually you preserve classical equations. When you fix a gauge, you just add an extra condition, not add it with Lagrange multiplier. In part, at the quantum level, you can do that, but not classical. So yeah, so for fluctuations, it will be fine if you add delta functions, say.
So, was the question answered?
The point was that you said already the right the right word.
Okay.
That Lagrange multiplier should be 0 if this is a gauge
On the classical solution. Okay.
Yes.
So let's proceed. How to disable drawing such way. Okay. Let me briefly discuss our old, not very old, but previous works on generalized unimodular gravity in a non-covariant setup. Generalized unimodular gravity exhibits some remarkable properties. So after a transition to ITMP 3+1 variables and after resolution of the constraints and after Legendre transform, the total Hamiltonian action takes the following form. It has a three-dimensional metric, shift function, and the corresponding conjugate momenta as phase space variables, and also it has ui as a Lagrange multiplier because near the momenta conjugated to lapse function, or sorry, shift function, because shift function is not dynamical. So as in usual case, we should test this primary, so-called primary constraint, whether it conserves under the time flow. So we should write down the equations that pi is conserved. After that, we found that generators super-Hamiltonians, spatial super-Hamiltonians, which is the generators of spatial diffeomorphism, is conserved, are conserved. So next, we test the conservation law of this secondary constraint, and at some step, we found that the result of conservation law is multiplication of one function over first function over some second function. So we have two possibilities, or one function equals to 0, or the other function equals to 0. So the full set of such equations constitutes the full set of Hamiltonian constraints, and this chain break. It's not an equation on the phase space variables, but an equation on Lagrange multiplier U. So since this chain bifurcates, we see that phase space decomposes into two subspaces with a different number and class of constraints. So in the first case, we have 7 first-class constraints which commute, which is other and generates diffeomorphism invariance. And using the general formula, which evaluates the number of physical degrees of freedom as the function of total flat space variables and a number of first and second class constraints, we found that in this branch there are only 2 degrees of freedom, while in the second branch there are 3 degrees of freedom. It can be shown that these 2 degrees of freedom of first branch corresponds to 2 graviton polarizations. Sorry. And in the second case, there are 2 graviton polarizations, usual, and plus something new, plus some additional degree of freedom. So we can test what is the role of this additional degree of freedom. We will do it on the Friedmanian background. So we can write down the analogy of Friedmanian equations, where the right-hand side comes from the fact that there is no 0,0 component of Einstein equations, because one of metric coefficient is fixed by the constraint. So the capital C is a constant of integration of spatial Einstein equations. So being integrated, this spatial Einstein equation becomes an analogy of Friedmanian equations. So
sorry, Nikita, may I ask a question about, is it necessary to take such a complicated background? Maybe it's just sufficient to take a flat space and examine the role of this third degree of freedom.
Okay. It can be shown that flat space example always corresponds to this first type of this first branch. So on the flat background without matter, we always have this T equals to 0, because T proportional to C, and we have no additional degree of freedom.
So you need to take a background with less symmetries to examine this mode, right? Because flat background is maximally symmetric.
Maybe because of symmetry of background. I don't know how to answer this question in this way. I think the reason is that on flat background we always have the first branch, which has only 2 degrees of freedom. So
have this capital C equal to 0 in the last equation, in the freedom equation.
In the freedom equation, C can be 0 or non-zero, and if we set C to be 0, we obtain the first branch, and if one takes non-zero C, one obtains the second branch. Is it an answer?
Yeah, it's pretty strange. Okay.
Uh,
The other question, what would happen if you have unimodular gravity in this case?
So in unimodular gravity, we have this denominator equal to 1. So in unimodular gravity, we have this result. So that it's proportional to lambda.
Okay.
Where lambda is the cosmological constant or the Lagrange multiplier?
Cosmological. In unimodular gravity, the role zero mode of Lagrange multiplier, plays the role of cosmological constant. It is the same thing.
Okay.
So let us consider arbitrary metric perturbations on this Friedmanian background. So after we have tensor perturbations, vector perturbations, conformal mode, and another scalar perturbation. So shift functions also can be decomposed onto scalar part, longitudinal, and transfer part. So after resolution of the constraints and gauging out non-physical degrees of freedom, only conformal mode psi survives, and it has the action which is usually called Mukhanov-Sasaki action. And the parameters of this Lagrangian can be computed from the n of gamma, which is the functional parameter of the theory. So the idea is to test whether this degree of freedom can be responsible for primordial scalar CMB perturbations. And we found that if we restrict ourselves to about 60 folding inflationary stage, flatness of spectrum tilt, and the absence of mass and gradient instabilities, we should fix the functional parameter for this theory as follows. So mass.
Nikita, you did not define W.
Okay. W equals to 2 times logarithmic derivative of n of gamma. Oh, sorry. N of gamma d logarithm gamma. So.
And what is eta in this Mukhanov-Sasaki action? The first integration variable.
Where
The first integration variable in the Makhlanov-Sasaki action.
it's conformal time.
Okay. And prime is derivative with respect to each, right?
It's derivative. Okay, yeah, it's the derivative with respect to conformal time. So this type of
sorry, and what is S as an index of C?
What letter?
S subscript of C. And the
This?
last term, psi nabla psi, you see psi nabla psi with prefactor, yes, C squared.
It's speed of sound, and it can be reconstructed from known n of gamma.
I mean S, not C.
S?
Yes.
Sound.
Okay, thanks. Okay.
Okay, if we take gamma, we will obtain, we will satisfy these restrictions.
Nikita, maybe you should also discuss the domain of stability of this theory. Non-ghost nature of this extrascalar mode is important, so I think this is important.
I think I briefly discussed, because the mass gradient instability conditions leads to z squared more than 0 and c squared more than 0. What do you mean? What additional comments should I give?
Well, yeah, that's sign restrictions on this combinations.
I think it's not very important for my talk. So let's proceed.
Sorry, but
now.
Sorry, what do you mean by ghost or mass when you talk about something which is not Lorentz?
Okay. Z is usually called mass parameter, and it carry sign between sign near kinetic term. So if it's negative, it would be ghost, and the same words about gradient instabilities. We want to have definite. We would like to have definite prefactor between gradient term. Is it an answer?
And what's meaning physically? It's instability in which way?
If we have such instabilities, the modes would diverge, I think.
Well, that's a usual either ghost or gradient instability. So if you have z squared negative, then this is the situation of the ghost field. When CS squared is negative, which is also possible depending on the choice of this initial function n of gamma, in principle, this coefficient CS squared can be negative. Then you will have gradient instabilities. It is quite interesting that in this model, well, usual situation, when you try to extract extra mode from the gravitational sector, you usually, the third polarization is bad because it is either a ghost or whatever. This model is good in the sense that there is a non-trivial range of unitarity of this model where both coefficients are positive. And this is a restriction. The sign of CS squared should be positive and the sign of Z squared should be positive. And they both are given in terms of particular combinations of original function n of gamma and its derivatives.
I guess the question was, what's wrong with negative z squared? This is the Gauss situation. This means that the energy of a particle corresponding to this psi is negative, okay? So very high momentum particles can have arbitrarily large negative energies, okay? High spatial momentum particles have very large and negative energies. And then you can create pairs of these particles and you destroy your vacuum immediately.
Yeah, absolutely, yeah.
I think that if that was the question, then the answer is it's catastrophic instability because you are allowed to create particles corresponding to this psi in arbitrary numbers together with conventional particles.
Yeah, so maybe when you like let it interact with something which has energy bounded from below, and this thing has energy bounded from above, right? You can create pairs.
Валерий Анатольевич, you turned off your microphone.
Since you can have arbitrarily high spatial momentum, then your energy of a given particle may be arbitrarily large negative, right? So you can create immediately create pairs of these particles, and essentially because of the infiniteness of the volume of the Lorentz group, your vacuum is catastrophically unstable. It decays immediately.
Okay, thank you.
Oh, I think I can proceed. So now we would like to reinterpret these results in covariance stuff. For this purpose, we resolve this constraint as follows. It's
can I ask a question about the previous slide? What happens if I tend the capital C, the constant corresponding describing your solution, if you move it towards zero?
I think you approach strong coupling regime, which can be described by perturbation theory.
Where does it seen?
So it is because initially this variable by means of background equation is proportional to C. So we can rewrite it as follows only when C is non-zero, C capital.
Okay, so okay.
We have C as prefactor of scalar mode action in some sense. So
basically, this is not exactly psi there, right?
Why?
Because Z is written up out here, right? And it doesn't involve any C. Z square is written just nearby your action, and it doesn't involve any parameter C,
right? It's correct answer only by means of background equations. If you straightforwardly do your perturbation theory, you will obtain something like C over R squared.
C over what? C divided by what?
Hubble constant. So
yeah, but this is by your field equations. It's just a ratio which is constant if you set your C to 0.
Maybe not this power of H.
Okay, then that is not should depend on C, right?
Mm.
Okay, anyway.
Okay, maybe I forget this calculation point, but
Okay, anyway. Okay, go ahead.
okay, thank you. So we would like to reinterpret these results in covariant setup. For this way, we rewrite the constraint as follows. So next we write down the stress energy tensor, and next we will find non-trivial property of this stress energy tensor. Being projected to the linear space orthogonal to comoving vector v mu, it becomes the following equation on lambda. The only solution of this equation is lambda is some function k of phi 0, because the only null vector of this matrix is the mu phi 0. So we find that this restriction tells us that d mu lambda proportional to d mu phi 0, so that lambda should be some function of phi 0 and maybe some integral of motion, which doesn't depend on the coordinates, space-time coordinates. Okay, it's very non-trivial part of this work, because next we try to exploit this equality. Indeed, we can write down reaction of the action with respect to phi 0 and found that it takes the form of Lagrange equations of some k-essence theory with Lagrangian written below. Again, we can obtain the equations of motion following from this theory for phi 0 field, and Einstein equations from this equivalent action, which doesn't depend on special Stackelberg fields. It is the statement of the duality of initial theory written by means of Lagrange multiplier and Einstein on written by means of Einstein-Hilbert action equipped with some kind of constraint on metric coefficients. So if we are not interested in special Stackelberg fields, which can always be set to spatial coordinates, we obtain that dynamical content of our theory can be described by the following k-essence actions. In general, k-essence have slightly
question.
Yep.
In your original formulation, you have the constraint that your n is equal to or whatever. I mean, in the previous transparency, you have this constraint.
P of x equal to
Right.
Z.
That. Yes. Yes. Where did it go on? Where is it in this formulation?
Where is what?
It's constraint.
The constraint it
Here you don't have any constraint. You have a rather arbitrary function k of phi 0.
The constraint is gone.
We
Because
resolve
this new metric G mu nu already does not satisfy any constraint. This theory is generally covariant explicitly, manifestly.
I can answer.
Of motion in your original theory was this constraint. Now you claim that that constraint is not satisfied here.
We can satisfy it in some in some sense. So we always should choose or constrain spatial Stackelberg fields such that the constraint is satisfied. We can resolve this constraint by means of special Stackelberg fields.
Okay, but this is not what happens in your new formulation, right?
In the we have two ingredients. The first ingredient is that on this shell, T mu nu and equations of motion for phi 0 doesn't depend on special Stackelberg fields. So special Stackelberg fields are decoupled from the dynamics of phi 0 field. Next, we can treat this constraint as follows. It constrains special Stackelberg fields as some function of gradients, I think, of temporal Stackelberg fields phi 0 and metric coefficients. So in the new formulation, the constraint is resolved.
How is it resolved? I don't understand. I mean,
well,
we treat it as an equation on special Stackelberg fields. We always can choose it such that the equation is satisfied.
In this covariant formulation, the constraint becomes just a gauge condition.
now
One of the gauge conditions fixing the general covariance.
I don't understand. Where is this gauge condition, whatever call you, this constraint in your new formulation?
Because the metric G mu nu no longer satisfies this constraint. This constraint appears if you identify phi a with the coordinates, then in this distinguished coordinate system, this constraint will reappear. And this will be just one of the gauge conditions fixing the freedom in diffeomorphisms.
No, the question is, are equations the same? All equations of
absolutely.
The equations are absolutely the same if we are not interested in special Stackelberg fields.
And because, if we are interested,
because they are resolved by means of constraint.
So in your new formulation,
in my new formulation, we resolve the constraint. We has not we have not special Stackelberg fields.
Okay.
In the new formulation, we have only temporal Stackelberg fields, which which can be interpreted as a scalar field of some k-essence series with the following Lagrangian.
Okay.
But the correspondence between our generalized unimodular gravity in covariant setup and this k-essence theory is not complete in some sense, because k of phi 0 can contain some part of initial conditions which were used when you try to find this k of phi 0. So it means that in the new formulation, in terms of k-essence, you should use the same initial conditions as was used in the procedure of reconstruction of k of phi 0. So in other words, you have some set of initial conditions for initial theory, and it led to equivalent some k-essence theory, which depend on these initial conditions. One initial conditions, one k-essence theory, one k-essence Lagrangian. Is it clear or not?
Not for all.
Maybe
It is clear, but the question is, how do you see that in the at the level of your original field equations? How do you see this freedom at the level of your original field equations?
Which freedom? I think we have not freedom but restriction on.
No, you have a freedom to choose k of phi 0.
We have no this freedom to. It can be reconstructed by means of Einstein equations of original theory. We claim that chi of phi 0 can be completely reconstructed by means of initial conditions and function pi of p of x.
Right. So the question is, where is this freedom in the choice of k?
There is no freedom. This freedom is equivalent to freedom of initial conditions of original theory.
Where is this seen in the original formulation?
Where is what?
Where is this? Is it seen in the original formulation that your complete dynamics has this freedom of basically of choosing this one parameter family of functions k, an arbitrary function k of phi 0? You see, where does it come from in the original formulation?
Again, chi of phi 0 is not arbitrary.
Well, it is. It depends on the initial conditions, right?
Yeah, right.
So by choosing initial conditions, you can choose arbitrary k. Where is this?
No. I think the space of function has is space of function of one variable is less than space of initial conditions.
I don't understand. Where is this freedom in the original formulation? You see, where is this freedom that you can have a number of different solutions depending on the initial conditions, and these solutions are parameterized by this k.
In the original formulation, we have one of the configuration space variables lambda. It do depend it does depend on initial conditions, as
And there's no
as all the variables.
Is there equation for this lambda?
This lambda is included to Einstein equations as prefactor of stress energy tensor.
Basically, you say it's an arbitrary function of phi zero.
It's not arbitrary.
On your solutions.
It's not arbitrary. It should be formed from the Einstein equations in some way. I don't know this way in the general case, but in the next slides I will demonstrate it on the example of Friedmanian background. Maybe the picture will be more clear on the particular example.
Okay. Okay.
Well, generally, the situation is resembling the situation in effective field theory. So suppose you're integrating out some fields and you get effective field theory with these fields integrated out. Integration these fields out means that you express these fields in terms of the remaining fields from equations of motion. But this expression might depend non-trivially on initial conditions. And then this initial conditions start entering the effective Lagrangian.
No, I'm sorry.
That's exactly the situation here.
You can't integrate out fields if the solution to your equation for this field depends on initial condition. It's not allowed. This you never do.
Why it is not allowed? In principle, initial conditions or boundary conditions, they enter the Lagrangian. For example, asymptotically flat boundary conditions, they enter the definition of the Einstein-Hilbert action in asymptotically flat spacetime. Maybe this is a trivial situation. Here, the situation is more complicated. Well, of course, you can consider this situation somewhat contrived. But well,
I'm asking a very simple question. If total set of solutions of your original theory and the new theory is exactly the same, then this arbitrariness in the function k of phi naught must be present also in the original formulation. Okay. So my question is,
no, what is present in the original formulation, the set of initial conditions, and the equivalent theory has a function k of phi, which parametrically depends on these initial conditions. It is it's like this, and this k of phi is determined from the solution of equations of motion of the original formulation. That's of course a flaw in the whole construction.
I don't understand this, but okay.
I guess that the best idea is to proceed to an example and test your arguments on the particular example.
Okay.
So we choose a flat Friedmanian background, and we set special Stackelberg fields to be special coordinates, and we set temporal Stackelberg fields be arbitrary function of t, and lambda is also a function of time. So we use initial formulation in terms of Lagrange multiplier and Stackelberg fields, where the part of them are fixed, but phi zero is not fixed. So the constraint takes the following form on this background, and next we exploit equation of motion of phi zero field, which is translationally invariant and can be easily integrated as follows. So using the definition of W, which can be reconstructed from pi of x, it is pi of x over 2 pi differentiated by x minus pi of x. Okay, we found the following equality, where c is an integral of motion. It is a part of initial conditions which we discussed before. The idea is that x depend on time, and also phi field depend on time. So we can express by means of some differential equation x of phi, and substitute here in and obtain lambda is some function k of phi 0, or k of phi in our notation. Can I proceed?
Say it slower.
Sorry?
Can you say it in more slow? So you have this equation between lambda and some combination of x. And
okay, we obtain this equation from the shift invariance of phi field, or its equation of motion.
Okay.
Now x is the kinetic term.
Right.
But it's also some function of time, and phi of t is some function of time. So
yeah, but you don't know them yet.
We will obtain them. So it's just idea. The idea is to express x as a function of phi and substitute here. Let's do this program. So we can write down Friedmann equation, which corresponds to variation with respect to lapse function. Substitute here lambda equal to c times w of x. Next, we divide Friedmann equation by x, take its square root, and find the differential equations which which expresses phi as a function of a. X should be substituted from the constraint equation. Remember that constraint equation.
I'm sorry, wait. How do you get the equation which doesn't involve time derivatives?
This equation can be expressed as follows: d logarithm a cubed dt equals to pi p of x divided by Planck mass. Okay, next we divide it by d phi, which also equals to minus x squared.
Yeah, okay.
Okay.
Mm-hmm.
Then we obtain this differential equation which evaluates phi as a function of a. So x on the right hand side should be evaluated as a function of a by means of a constraint equation. So this equation can be integrated. So we can do the chain of substitutions. We have lambda as a function of x. Then we substitute here the constraint equation, which expresses x as a function of a. Next, we exploit the solution of this equation and substitute here a as a function of phi. then we obtain lambda as a function of phi, or by our definition, it's k of phi. So we found k of phi, and it does depend on initial conditions contained in C capital.
No, but this is just a number C. It's not a functional freedom.
It's not functional freedom. It's parametric dependence on initial conditions, as we
Where
said
do
before.
the initial conditions come in?
Sorry?
I don't understand. I'm sorry. Where is the functional freedom? In your calculations, I don't see how you can
There
have.
is no again. There is no any functional freedom. There is
Phi is not an arbitrary function, right?
Is not arbitrary, but it has a parametric dependence on initial conditions.
It has two parameters,
which we represented by C in this formula.
What is K of phi? Can you write explicitly what is K of phi?
No, we can do this calculation for particular phi of x and write down the explicit form of chi of phi.
So,
K of phi.
Nowhere you get functional freedom. Which functional freedom do you have here? What?
We will not get any functional freedom.
Your K of phi is a function of a few parameters: a naught, phi naught, c, right? What else does it depend on?
K of phi is some concrete function,
which involves a few
phi.
parameters: phi naught, a naught, and c, right? That's the only parameters I see on your slides.
The only parameter is c.
Right. So the question is, how can you have it, this K of phi, arbitrary function, sine, cosine, tangent, hyperbolic, etc.?
Okay. The initial theory has pi of x as functional parameter. Next, we do some calculation and reconstruct chi of phi.
But this P of x also is included in your new formulation, right? It doesn't.
It's also included.
Right. So suppose I have P of x known.
Yeah.
Fix it like, x squared, x cubed, whatever. Okay. Then this K of phi is not arbitrary any longer.
It's not arbitrary. It can be reconstructed from pi of x and has one parametric dependence on this function of.
Okay, but in your new formulation, this K of phi is arbitrary function.
Not. It's not the case.
If you go back to your slides, this K of phi, which was arbitrary, K of phi not. Yeah, this one. Yeah.
Here it's not arbitrary. It can be. It should satisfy. It should be chosen in such way to do Einstein equation satisfied.
Then this is not K essence.
This is not K essence, but equations of motion can be rewritten in such a way that they are equation of motion of chi essence.
Can you go next slide, please?
Okay.
Yeah, what is K of phi 0 here?
It is K of phi 0, which can be reconstructed from the equation of motion of initial theory.
Sorry, it's action. If it is action in the second formula, then this K of phi cannot be reconstructed by solving any equations. It's action. So K of phi either is specific.
Okay. Let's draw the diagram.
Sorry for interrupting you, but we are running out of time, so let's maybe go through main points.
Okay, I'm sorry. sorry.
Yeah, and try to finish within, let's say, 15 or 20
Okay,
minutes.
okay. I maybe I can proceed to and after I finish the presentation, we will discuss these points. Okay,
Okay.
Валерий Анатольевич.
Nikita, just demonstrate this exactly solvable example.
Okay,
Just the
okay.
answer.
Let's demonstrate the example. But it's demonstrated in non-constructive way, I think. So there is exactly solvable example where the construction of the reconstruction procedure of function k of phi can be done explicitly.
Don't explain the procedure, just give the answer.
Okay, we have
P
phi
of x, what is k of
we
phi?
have this phi of x.
Nikita,
Next, we do the calculation and found that k of phi is the following function, concrete function with the one parametric dependence on c.
Nikita, один момент. I'm sorry. We need to kind of wrap up. Could you just summarize main results, and then those who are interested in details could stay longer?
Okay.
Otherwise, the seminar becomes indefinite.
Okay. So we have some examples where this reconstruction can done. The one of them are exactly solvable when we exactly reconstruct chi of phi. The next example is the example of linear phi of x. It's interesting because we can do the change of coordinates. After that, the corresponding Kaysen's Lagrangian becomes just canonically normalized Lagrangian of some scalar field. We cannot reconstruct this potential explicitly, but we can draw this. We can draw the picture of the potential. So there are two solutions of constraint, and one plot correspond to one solution. So the last example is example corresponding to our n of gamma, which corresponds to observable CMB spectrum. So we can reevaluate phi of x from known n of gamma, which we set from the some restriction on CMB spectrum. So we can write down phi of x, and we can write down k of phi. The result is interesting because being decomposed into series of small spectrum tilt, it looks like radiative corrections. It looks like some radiative correction because of appearance of logarithmic terms. It can be interpreted as follows: that our theory is some effective theory found by integrating out some degrees of freedom in ambient theory. So we remember that this type of constraint is not only one type. So there is another type of constraint which leads to a stress energy tensor, which has the form of perfect fluid stress energy tensor. And in this case, decoupling of part of Stackelberg fields also takes place. Again, we project stress energy tensor on a comoving vector of this fluid, and we obtain that in this case lambda is not function of temporal Stackelberg field, but some function of spatial Stackelberg field. So the equation of motion can be obtained from the following action. It has a part which algebraically depend on spatial Stackelberg fields and some kinetic term. It's in literature such type of Lagrangian called effective perfect fluids, and may lead to inflationary models which can be consistent with observed CMB spectrum. You can see this article for its details. So let's conclude what we have done. We introduce maybe new idea of modified gravity theories, which differs from general relativity by some constraint on metric coefficients. Because of this fact, I call it constraint modified gravity in this talk. So next, if we restrict this constraint to the such class of function which it parameterizes to the function which leads to rotational invariant Lagrangian and also perfect fluid stress energy tensor generated by this constraint term in the Lagrangian. We found that there are only two classes of such function which parameterize the constraint. And next, we examined this type of constraint. The first turns out to be equivalent to generalized unimodular gravity, which has interesting, I think, cosmological application and interesting theoretical properties from the point of view of Hamiltonian constraint theory. So next, we found that in some sense, generalized unimodular gravity in a covariant setup is equivalent to K-essence theory. The Lagrangian of this K-essence theory can be reconstructed from the functional parameter of initial generalized unimodular gravity theory. Okay, and finally we briefly discussed the second type of constraint which leads to perfect fluid, rotationally invariant perfect fluid stress energy tensor, and found that it also corresponds to some known models, as generalized unimodular gravity is equivalent to some K-essence theory. What points which were not discussed in this talk in our works is the addition of motor content. The second is that we do not discuss graceful exit issue in the inflationary model of generalized unimodular gravity. And finally, we didn't discuss the models of constraint modified gravities which doesn't correspond to perfect fluid stress energy tensor. So this brings me to the end of my presentation. Thank you for your attention.
Thank you for your talk. Are there any questions?
Nikita, may I ask a question?
Okay. Yep.
Okay, so could you please explain for non-experts what is special about this K-essence theory and why it's good to have this duality of your theory with K-essence theory?
I think I can explain it as follows. The nature of K-essence scalar field is not clear. In this work, we claim that K-essence scalar field can be the part of metric degrees of freedom.
I'm sorry, I have even more general question. What is K-essence?
So K-essence is a rather general scalar field theory. Lagrangian of K-essence field theory is some function of kinetic term and field. X stands for kinetic term of scalar field phi.
And
so
what's the reason why we need to consider such theories?
So such theories mainly used in cosmological content. It was shown by Mukhanov that it was introduced by Mukhanov. It was shown that such theories can be responsible for inflation and perturbation of this K-essence field can generate scalar primordial perturbations.
So it means that this theory is of physical importance, and you are looking for a kind of duality of your theory with this physical grounded theory, right?
Right.
Okay, thanks.
Any other questions?
I wanted to ask one thing. So about motivation, you start from, so you use a constraint which anyway breaks general covariance. So then I wonder, why do you take the Einstein-Hilbert action as the first term? Because if you don't care about symmetries, general covariance, then you can write many more like other terms.
I think the most of modified gravity theories have Einstein-Hilbert term as one of the term of the full action, because we first of all we need to describe usual physics, which can be successfully described by Einstein-Hilbert term in intermediate scales, scales of galaxies, I think, on our Earth. So at least perturbatively, modified gravity theories should contain Einstein-Hilbert term in some sense to be consistent with experiment.
But are you sure that the constraint that you have doesn't spoil like simple tests?
What does it spoil?
like simple experimental tests, like I don't know, solar system tests.
Again, it can be proved that any solution of general relativity is a solution of our theory, but the converse is not true. There are any other solutions, so that such constraint can spoil the common test of general relativity.
Okay, thank you. So are there any other questions? Okay, it seems that we don't have any more questions. So thank you, everyone, and I'll see you next time.
So, Valery Anatольевич, maybe you want to continue the discussion or not?
I will have to take a look at the paper because your statements in the middle of your slides are sort of contradicting to what you were doing afterwards. So yeah, this kind of disclaimer in below, saying that your